Newton's second law states that the rate of change of momentum of an object is directly proportional to the force applied, and that object moves in the direction of the force applied. And the momentum of an object can be defined as the mass of that object times its velocity. Let's consider these two objects, say A and B. Now suppose A moves at a velocity, say v1, while B is motionless, so this velocity is 0. Now when A starts moving, it applies a force on B which makes it change its velocity from 0 to a velocity, say v2, and B gains momentum as its mass remains intact and its velocity is increased. This is the idea behind the momentum optimization algorithm. The search process, which initially looked like this, where we're looking for this best values of theta, which actually minimizes the value for the loss. We're supposing the loss is minimized when we get to this point. Now turns into this. So we have something like this instead now. So the search process has gained some momentum and turns out now to go or to find the best values for theta faster. Now let's look at this algorithm critically. We have, for the very first step, we let a v to be equals epsilon v. Now this epsilon is a hyperparameter which can be tuned. Now, and the bigger the value of epsilon, the more the algorithm kind of goes faster towards the best loss or minimal loss. Now we have v equals epsilon v minus alpha. This alpha is a learning rate. So we have, if we have epsilon v taken away, in this case we have v equals negative alpha, the partial derivative of the loss with respect to theta. And then we update our parameters theta by theta equals theta plus v. Now notice that if this part is taken away, we have v equals this. So basically we have this stochastic gradient descent algorithm where we had theta equals theta minus alpha partial derivative of L with respect to theta. But when this is included, we have the momentum optimization algorithm, wherein the greater the epsilon, the more this, or the faster we go towards our minimal loss. Now let's see how this affects V. When we make V the subject of the formula in this equation, we have this. So we have taken this to the side, we have V minus epsilon V, and then dividing all through by 1 minus epsilon, we have this. This is V equals alpha times the absolute value of partial derivative of L with respect to theta divided by 1 minus epsilon, such that when epsilon equals 0.9, we have V equals 10 times alpha times the partial derivative of L with respect to theta. So we'll see here that instead of working, like in this case, instead of working with alpha times the partial derivative of L with respect to theta as in gradient descent, we're working now with 10 times this. So the speed of the particle, in this case, this training algorithm, is increased 10 times. So this tells us that the greater the value of epsilon, and which an epsilon actually ranges between 0 and 1. So the greater the value of epsilon, the more epsilon approaches 1, the more momentum the algorithm gains. And the more it approaches 0, the less momentum it actually gains. So if we want to work with 0 momentum, we just have to take epsilon to be 0. And obviously this part is going to be taken away. In the case of Nesterov momentum, this computation of partial derivative of the L with respect to theta is done with an updated theta. So unlike here where we just use the previous value of theta from the previous epoch or from the previous batch, in this case we have to update theta first before taking this. So in this case we have theta prime, which is equals theta plus alpha times V, and then we do V equals epsilon V minus alpha times the partial derivative of L with respect to theta prime and not with respect to theta. And this brings some correcting factor in the computation of the parameters. Now we shall implement the momentum algorithm, and you shall do the Nesterov momentum algorithm as an in-class exercise. So you're advised after looking at this to do same for the Nesterov momentum algorithm and before continuing to the next section. So right here we have the number of epochs to be 200. We have the learning rate, the value for epsilon, the batch size. We have now two values for theta. That's theta SGD. That's when we're working in stochastic gradient descent algorithm. Theta for the momentum algorithm. We have V SGD, and then we have V momentum. It should be noted that for V SGD, actually, what we're doing here is what we're considering V to be negative the learning rate times the partial derivative of L with respect to theta, as we saw here. So here it's kind of like the same as the gradient descent algorithm. Whereas for V momentum, that's what we initialize here, we have epsilon times V, as we saw in the slides, minus this. So it's minus actually this. Whereas here we have theta SGD, and here we have theta momentum. So we are having different values for theta, whether it is SGD or in the case where it is momentum. Then as usual, we have for all the range, that's for all epochs, and then for all B in range 0 to length of X, and taking steps of the batch size. In this case, we're considering our batch size to be all the data set. So we have this. And then we update our partial derivative of the loss with respect to theta. So we have the theta SGD. So this is partial derivative of the loss with respect to theta SGD. And this is partial derivative of the loss with respect to theta momentum. And here we have this and this. So it's kind of the repetition of the linear regression algorithm we saw previously. So we've seen this already. And then we update our theta. Notice how here this actually is the same as what we've done already. So this V SGD, when replaced here, is kind of the same as doing simply minus this. So we should take this from here and fit here. So the same as doing this. Let's take some step back. We had this 200. Okay. Now that we have that, we also have the epoch loss SGD, the epoch loss momentum, which is the same. And then we could simply plot for when working with SGD and when working with momentum. We've changed the color to red for when we're working with SGD, and when working with momentum, the color is blue. While we recall that the optimal solution is when we have 8.71 and 1.01. We could run this, and then we have this as results. So we'll see clearly that after 200 epochs, the momentum algorithm has already achieved or has already gone very close to the required results, if not even the results itself. No, it's almost done. So we have SGD, which is still lagging, while momentum has already achieved the results. Now we could add this to 2000. We see that finally, even the SGD hasn't yet gotten to the correct results, and the loss of momentum is smaller than the loss of the SGD. We run this. So our values, we now modify epsilon, our hyperparameter. We could take, say, 0.5. And we'll see clearly how the reduction of this value of epsilon has slowed down the momentum algorithm. So you shall take the Nesterov momentum algorithm as an in-class exercise. For the next three algorithms, we are going to deal with algorithms or optimization algorithms which have adaptive learning rates. The very first one is the Adagrad optimization algorithm. We have a variable R which varies depending on the partial derivatives of the loss with respect to the parameters theta. Now, this is an adaptive learning rate algorithm because, as we can see in this update, the learning rate, that is alpha divided by sigma plus square root of R, actually depends on the slope partial derivative of L with respect to theta. So when we have this partial derivative of L with respect to theta large, the learning rate actually reduces. It should be noted that this symbolizes element-wise multiplication. So this is the same as the partial derivative of L with respect to theta squared. On the other hand, for small values or for smaller values of the partial derivative of L with respect to theta, this learning rate increases. So what we're trying to do here is, suppose we have this kind of bowl. As we approach this point with the smallest loss, the learning rate increases. So we tend to go faster when we are almost finding this smallest or minimum loss. But this is a great idea for convex functions where we just have only one point, or rather only one minimum turning point. For non-convex functions, which in the case of deep learning we always kind of encounter, this Edergrad algorithm will tend to kind of go quickly and converge even in the local minima. So this is not the best optimization algorithms, or this is not a very popular optimization algorithm for deep learning problems. Let's look at the code for the Edergrad optimization algorithm. We define theta Edergrad, we define R Edergrad. Since this time around we're dealing with R instead of V. We define the loss Edergrad, epoch loss Edergrad. We have the theta Edergrad, which is a function of theta Edergrad. We have R Edergrad, which is R Edergrad plus d theta Edergrad times d theta Edergrad. Recall that this multiplication is element-wise multiplication, whereas this is actually matrix multiplication. Then we have theta Edergrad minus equals, that is to say theta Edergrad equals theta Edergrad minus the learning rate divided by sigma plus square root of R times the theta Edergrad. As usual, we have epoch loss Edergrad, we have loss Edergrad, which is appended, and then we have our plot. So running this is what we have. We'll see here that the Edergrad algorithm has the worst performances compared to the others, and it's printed in green color. It may not be very visible. So if we take out this, we have this. The next optimization algorithm is the RMS prop. Here it goes. Similarly with the Edergrad with its variable learning rate, RMS prop 2 does this. But the difference here happens in the number of past partial derivatives we rely on to modify the learning rate at a given instance of the gradient descent algorithm. So with Edergrad, for example, what we do is we keep on adding this to R. So as we go on with the algorithm, we continue adding up these R's, and that's what affects the learning rate in the gradient descent step. Whereas here we have this quantity rho, which modifies the reliance on past partial derivatives to affect actually the learning rate at a given gradient descent instance. And the RMS prop optimization algorithm happens to be one of the most used algorithms in deep learning. Let's look at the practical development of the RMS prop algorithm. So here we have rho, which is defined. This is a very typical value which can be tuned depending on how much in time you want to go back in using the partial derivatives with respect to theta to affect the current learning rate. We have sigma, which is this, the batch size. Here we have theta RMS prop. We have R RMS prop. We have the loss RMS prop. And then the epoch loss, the theta RMS prop based on theta RMS prop, R RMS prop, which is rho times R plus 1 minus rho times R, or rather 1 minus rho times d theta times d theta. Remember, we had this element-wise multiplication in the slides. And then here we have theta RMS prop, which is equals theta RMS prop minus the learning rate divided by the square root of sigma plus R RMS prop. Unlike with undergrad where we had sigma plus the square root of R, here's the square root of sigma plus R RMS prop. Now note that the sigma, the value of sigma is taken to be this small because actually sigma isn't one of the hyperparameters to be tuned. Sigma is just here for computational stability. As one of the clear uses of sigma is that in a case where we have this value, say we have this value which is going to be 0, and that or rather this value, say we have our RMS prop which is a 0, and finding the learning rate divided by 0 is an infinite number. So to avoid that, we just simply add this 1 times 10 to the negative 6 term. So basically that's the use of sigma. And then we have times the theta RMS prop. As usual, we have this, and then we plot this. So plotting, we have something like this. So this is actually after 100 epochs. So this after 100 epochs, we could take this to 50 to see how they behave. Or let's reduce this. Let's say 20. Okay. We see how after 20 epochs, the RMS prop algorithm performs second best just after SGD algorithm. Now going to say 200, we have this. Now we have one of the best performances. It's actually even the best performance. We see that it actually gets this value which is needed. But the momentum algorithm seems to perform slightly better than the RMS prop in this case. Nonetheless, you have to note that RMS prop algorithm is one of the most used optimization algorithms in practical real-world deep learning. I'm playing around with the value for rho. Say we take 0.7. Here we go. We have this. Now it behaves. It's kind of having worse results. So generally, we take rho to be 0.999 for RMS prop. So we get to have this better results. Now let's take rho to be 1. Let's see what it gives us. See, we have this. Let's take it to, let's increase this. Let's say we have this. So we see that even that doesn't give us the best results. So 0.999 kind of has. So this kind of what we call tuning, like we just not actually playing around, but moving these values a bit so that we could get the best out of the optimization algorithm. And the ability to do this is basically gotten after doing this several times. So depending on the problem you want to work with, you may want to use RMS prop or use momentum or just bear SGD out of your different experiences. So you're advised to always do the in-class exercises and work on many more projects so that you get all hands-on experience needed to be able to play around with hyperparameters like this very easily. In ADAM, or the adaptive moment optimization algorithm, we kind of add some momentum to this RMS prop algorithm. So this momentum is added via this S variable, as you can see here. So we have S, which is giving us rho 1 S plus 1 minus rho 1 times the partial derivative squared. Now note that rho 1 is a hyperparameter to be tuned, and as we will see, rho 2, another hyperparameter to be tuned. R is also equals rho 2R into 1 minus rho 2 times this. And we keep on adding the value of t as we go on. So we keep on adding this value of t because it's going to be used here. We have S equals S over 1 minus rho 1 times t, and R equals R over 1 minus rho 2 times t. And then what we do simply here is we have to update theta as theta minus S divided by square root of R plus sigma times the partial derivative of L with respect to theta. So here we are not only adapting our learning rate with respect to our partial derivative of L with respect to theta, but we are also including or adding up some momentum. Now, typical values for sigma, as we have been saying, is 1 times 10 to the negative 6. Typical values for rho 1, 0.9, rho 2, 0.999. And it should be noted that Adam is kind of like the most popular of all these optimization algorithms in practical. For our in-class exercise, you shall implement the Adam algorithm or the Adam optimization algorithm.